Welcome everybody to this weekly series in the Cognitive Systems Institute group sessions. And today we're very lucky to have Victoria Stodden, who's going to talk to us about advancing data-enabled research via reproducibility and transparency. So over to you, Victoria.
Well, thank you so much, Susan. It is really a pleasure to be here giving this presentation. A couple of things. My slides are available on my website. Stodden.net should be straightforward to find if you wanted to explore them on your own as we're going through. And I only have 30 minutes, counting down. So what I'm doing is taking what is a pretty broad topic, advancing data-enabled research via reproducibility and transparency, and I'm trying to distill it into really a couple of points. So let me just mention my agenda. So what I'd like to do today is try to parse the phrase reproducibility into three different approaches, and I think this maps some of the discussions that I'm sure you've heard that are going on in through the national press and in research circles and so on around reproducibility, and also is, foundationally different approaches to problems in reproducibility that lead to different remedies. So I think it's also quite important. Then I wanted to pull out what I think are four recommendations that are key for this discussion from the recently published National Academies report called Reproducibility and Replication in Science. This report seems to be getting a fair amount of attention, and as I'm sure you know, the problems around reproducibility and opportunities around reproducibility are also getting quite a bit of attention, so it's maybe not that surprising. And then I'd like to finish with a proposal that I think follows from the discussion that we'll be having today around how to reconceptualize the dissemination, sharing, and integration of the findings that we're producing from this data-enabled and computationally enabled research. So just before I start, let me tell you a little bit about who I am. I have a little bit of a different background. My PhD was in statistics. After I finished my PhD, I went to law school. Both of these events happened at Stanford University, so I was there for quite a while. I will mention as a curiosity that in the summer of 2000, I was actually an intern at the IBM TJ Watson Research Center. So there's some connection to the IBM folks here. Currently, I'm an associate professor in the iSchool at the University of Illinois at Urbana-Champaign. I have a number of affiliations on campus, including in computer science, statistics, at the law school, at the National Center for Supercomputing Applications, and in the Coordinated Science Laboratory. And the majority of my research is really focused on this question around reproducibility. I tend to zero in on computational aspects, on how we can enable reproducibility, what it means to leverage computation in discovery. It also touches on statistical generalization issues, policy issues related to reproducibility. They're all kind of knit together. So you'll see a little bit of that in the talk. Okay, so let me just move quickly to my own conceptualization of reproducibility is not one of bad actors, right? Your reproducibility coming from sort of poor science. I think we're doing better science than ever. And I think what we're doing is leveraging these opportunities to really advance discovery using all of the aspects of big data, big compute that have been coming online and accelerating science for the last 10, 20 years. And so the question that relates to reproducibility is, how do we recognize that this is fundamentally how we're producing scientific results, and what does it mean to reproduce a result that's been generated in a computational context? So for academic discoveries or published discoveries today, just about everything has some computational component in it. Even ones that may not report their computational assistance that they've received in their results often have computational work behind it somewhere. However, we just about never expose the computational work. There are notable exceptions to this, but generally speaking, we still publish in conference proceedings and academic journals as if it's 1970 or whatnot, and we have not actually used computational aspects in generating the results. So this mismatch is the way that I'm conceptualizing reproducibility, the way many people conceptualize reproducibility. So really it's, how do we catch up with the how quickly the scientific community has moved to adopt these technologies and accelerating their research and their discovery. So really, it's grounded in my mind as the source of opportunities that have been taken and a continuing stream of opportunities that are arising. So I'll make a note here around point 3. So everybody kind of knows big data, sort of big compute is accelerated, storage capabilities have accelerated. So we sort of see all these technological underpinnings that have really opened the door to much greater discovery and greater types of discovery. But one of the things that this means is that we are writing a lot of code that does this discovery. And as I mentioned, the code itself is not actually disclosed in general for scientific publications. And what this means is we have real intellectual contributions to science appearing only in the software. It used to be that these contributions would be appearing in the publication. And so now they're actually in the software itself, often not being made available to downstream readers and users. But it really has strong implications for the value of software to the scientific community from a scientific perspective, not necessarily from only a usability perspective or other types of leveraging that comes from software. So this really advances software to a first-class scholarly object, at least in my mind. So I will now parse out what I think are some useful ways to think about or make the reproducibility discussion a little more intellectually clean. And what I can do is provide one framework that can maybe help do that. So I split reproducibility into 3 categories. The first one is empirical reproducibility. And what I mean by that is reproducibility in the sense of lab experiments or experiments that are done at the bench, for example, the traditional type of scientific research that we have done for hundreds of years, where you would communicate to your colleagues after a discovery what physical steps you actually went through at the bench or in the experimental context. So this is sort of a very traditional notion of reproducibility. Now, as we've become more data enabled, statistical reproducibility has come increasingly to the fore. Now, what I mean by statistical reproducibility, essentially, are you using correct or appropriate statistical methods that allow these findings that you're publishing to generalize to new samples? And so this encompasses things like, have you even used, appropriate models? Have you used appropriate statistical tests? Are you doing things like running many statistical tests and cherry picking the ones that support your hypothesis going in, for example? That's one of the big problems in the p-hacking discussion. So statistical reproducibility, fundamentally, do we think that results will generalize from the data where they were actually discovered? So do we have sufficient power? Do we have correct experimental design? All these fundamental statistical questions, and this is I think a extremely pertinent issue because of the way data is now pervasive. So even traditional scientists in sort of empirical disciplines are now data enabled and finding themselves becoming statisticians very rapidly. The final area where I think there are unique issues attending to reproducibility is in the computational aspect. So I call that computational reproducibility. And here, roughly what I mean is, can I understand the statistical steps that were taken, the computational steps that were taken to arrive at that discovery, and would I be able to repeat them? Right, and this could include things like implementation of mathematical models, how the code was actually designed, written, how parameters and hyperparameters, if there are any, were arrived at, and so on. It could go even down to things like numerical reproducibility issues with floating point number standards in the actual lower level software, for example. So that's what I think of as computational reproducibility. And I think these are quite distinct ways of approaching reproducibility, and they each, when you sort of start peeling back layers on the onion, they each offer different remedies to problems that may arise in this area. So for computational reproducibility, I think it has a certain I'm not going to, I almost want to say obligation around transparency that conforms with approaches to scientific knowledge discovery. So traditionally we had two branches of the scientific method, right? Deductive branch with mathematics, formal logical structures, for example, and the second branch, empirical or inductive branch, where we carry out statistical analysis of controlled experiments. There's lots of talk. It's been going on for probably 20 years, at least, about how computation, for example, simulations and so on, and data-enabled discovery, particularly around big data, are essentially crafting third and fourth branches of the scientific method. Now on the slide, you'll see at the last point there, I put a little question mark. So the idea is that I want to prompt some thinking about is whether they really do rise to the level of a scientific method or a branch of the scientific method, and what that really actually would mean. So I'll just give a couple of examples here very briefly. So I just sort of grabbed these off the web. There are many examples. So on the left, we see a modeling and simulation workshop that was hosted at NIST in 1995. And they say that it's common now to consider computation as a third branch of science besides theory and experiment. So this was a sort of accepted and common in 1995. And then there's a fantastic book, actually, this book, The Fourth Paradigm, Data Intensive Scientific Discovery. It was this is a co-edited volume with chapters of lots of different authors. You just look in the preface and it says this book is about a new fourth paradigm for science based on data intensive computing. So this sort of situational rhetoric is clear, that computation, data-enabled research is also computational, but these technologies are really affording, the idea is they're really affording these new investigation methods. Okay, so why do we have the scientific method? Here's one idea. It's literally because we don't know what the answer is, of course, and trying to unearth this answer by doing research is fraught with error. So how do we actually know or have some confidence in the fact that our finding might actually be correct? So an argument is that the central motivation for the scientific method is actually to root error out and give us as much confidence as we can in the findings and the results of the work. For the deductive branch, so say in mathematics, you would not propose a theorem to the community without giving a proof, right? And there's a very clear idea in the community of what comprises and qualifies as a proof. So you can't sort of have some airy narrative and expect that to fly, right? There's sort of very clear definition of what that proof actually is, and that's part of disseminating knowledge to that community. In the empirical branch, there's a well-developed machinery of hypothesis testing, use of appropriate statistical methods. In a very structured way, you would communicate the method. So if you try to submit a paper to just about any journal and leave the method section blank, it won't even get read. I mean, they need to know how you actually got to those results. So here's the claim. The computation, data science present potential third and fourth branches of the scientific method until we develop comparable standards in disclosure and dissemination. So what's our analogy to the proof that allows people to understand and be convinced why a computational finding might be correct? And what information would we need in order to allow people to actually do that, similar to how the proof supplies that chain of reasoning for a mathematical theorem, for example. So I'll mention a quote that often comes up, also to give a hat tip to John Claerbout, who noticed these problems back at the beginning of the 90s. So John Claerbout was a geophysics professor. He's now emeritus at Stanford. And he's in the very early 90s, he put some standards together around disclosure of the computational methods for student theses that he was supervising. And he wouldn't sign the thesis until he effectively could hit return on his system in his lab and regenerate the results, and actually regenerate the whole thesis, including the figures and tables that were in there. So this he called really reproducible research, and it's distilled into something of a slogan by David Donahoe at the end of the 90s, where he says the idea of really reproducible research is that an article about computational science in a scientific publication is not the scholarship itself, it's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data that generated the figures and the tables that are being presented. Now, this raises a question sometimes here, which is sometimes the question is roughly along the lines of, well, who cares if you can hit return and regenerate results? It doesn't tell you that the results are scientifically correct. And it doesn't. That's absolutely right. However, it does allow you to determine whether the results are correct. Replicating the work, so suppose I went and took the same scientific question that you were interested in, and I re-implemented the methods myself. So I recoded them, got it working, got some results. So first of all, the results will not be identical to your results. So you will always have this question of why are they different? Is this just general differences in system, machine state, for example, that made some variability in a certain decimal place that really we just don't care about? It's not scientifically significant, so we just call it replicated. Or is this something that's very different, for example, in the way I've understood the methods or implemented the methods, where really I've done something wrong, or maybe I've done something innovative that's actually improved our understanding of the science. So without computational reproducibility or the exposure of those pipelines, it's impossible, almost impossible, to answer those questions and understand where there is error, if there is any, and who might be on the right track, and why these results are coming out actually differently. So my argument is we need both these re-implementations of the experiments as well as computational transparency or reproducibility in the experiments. Okay, so now on to the report. So because of these discussions that have been happening across society, there's been sort of front page headlines in the New York Times. Congress became very interested in issues around reproducibility a number of years ago. And they included funding for a reproducibility, Congress included funding for a reproducibility study in the appropriation for funding of the National Science Foundation. So there's $1 million set aside for this study. National Science Foundation asked National Academies of Science, Engineering, and Medicine to carry out the study. I was a committee member, so what National Science Foundation does is it will invite members of the community together to come to some kind of set of recommendations. They're published in what's called the consensus report. So this was published a few months ago this year. And the committee was called Reproducibility and Replication in Science, and so is the name of the report. And I linked here, that's the underline in the title, so if you're interested in the full report, please take a look, and it includes, for example, our charge, motivation, and other things I don't have time to get into here. But what I would like to do is pull out what I think are perhaps the most interesting parts of the report for this talk and this community. The first thing we did is we needed to address issues of definitions. And the definitions that we used in the report match the definitions that I had proposed to you at the beginning of this discussion. So reproducibility, also called computational reproducibility, obtaining consistent results using the same input data, computational steps, method, code, and conditions of analysis. And then we reserved replication to mean repeating the study. So replication, obtaining consistent results across studies aimed at answering the same scientific question. Now, in our few minutes, not to go into too much inside baseball and details, but different scientific communities had used different versions of these definitions, and we needed to align the definitions simply for our report for consistency, but also we thought this could be something that clarifies definitions across the community if people accept them. It looks like there does seem to be some acceptance of these definitions now, the way that I've written them here. This is copied directly out of the report. And just as a heads up, there's a lot of words on the next 4 slides because I've copied it for completeness right out of the work, but I'll just distill the key points from each of the slides coming up. Okay, so here's the first recommendation. This is our first recommendation. I think it's also the first key recommendation, which is share your stuff, roughly. So researchers should convey clear, specific, complete information about computational methods and data products that support their published results. Now, I just want to underscore that this is not normal today, right? Like I said, there are notable exceptions to this. There are many strides that have been taken in the community, particularly by some journals and some technological efforts, but this is not the normal way we can communicate results. The normal way is still in words or math in a PDF. So we want input data, detailed description of study methods, and when it says ideally in executable form, of course it means software. information about the computational environment where that study was originally executed, so we can understand what is scientifically meaningful, what is from the computational system, or even what information do I need to repeat the study and maybe get it working on my new data, for example. Okay, key recommendation 2 is that we thought that one of the issues in reproducibility that it would be productive to address is tooling, to allow the production of computationally reproducible results in an easier way, right? If people are clicking around in Excel, producing reproducible pipelines with your publication, according to our previous recommendation, it's a challenge, right? However, if you're using more sophisticated workflow software, for example, it might be easier. So can funding agencies and organizations who do scientific funding improve that aspect of generating and communicating computationally reproducible findings by investing in research and development of open source, usable tools and infrastructure that support reproducibility? I mean, if you think about it, Excel is accounting software, right? It wasn't designed for reproducibility or science or research in general. Okay, another blizzard of words. So let me just summarize that for you. So here's another key recommendation, which these are pointed towards the NSF. Our whole report actually was pointed towards NSF by designed by the very fact that NSF had funded this report through its appropriation. So it suggested the National Science Foundation should provide repositories in some way. Right, so where do you put the code, the data, and all of these computationally important artifacts that are coming out of the research? So that means, what could you come up with a set of criteria for trusted open repositories? Certainly we're moving beyond the idea of a lone researcher making code or data available on their website, for example. Could we do something that's centralized, curated, findable, and so on? And what does that really mean for the community? Harmonization with other funding agencies. So NSF is one of an entire ecosystem of scientific funders, and it would very likely be a benefit to the scientific community not to have too much divergence in demands that are being made on researchers and the types of research and affordances that were being supported. Endorse or consider creating code and data repositories for long-term archiving, preservation of digital artifacts that support claims in the scholarly record that NSF has funded. So create a there for people to make artifacts available. There are solutions now. They are not solutions, generally speaking, that were created for science in general. Once again, scientists are creatively repurposing other tools that are out there. I'm thinking about things like GitHub, Zenodo, for example, Dataverse. There are things out there, and so it's not like we're starting from scratch. But let's think about what that means to actually support archiving of these artifacts for the long term. NSF proposals require a data management plan currently. Could that data management plan be extended to things that support reproducibility more generally, like, for example, including the software, code, workflows, input information, and so on? And start thinking through and addressing problems around confidentiality, for example, privacy, aspects that make it more difficult to share data or even code, for example, for legal reasons and other reasons. Are there ways to think creatively about some aspects that could be shared or could be made available to limited groups, for example, to get some of the benefits of reproducibility, even if it's not possible to make all of these artifacts completely open? So we could do a deeper research dive there. Okay. This recommendation, the fourth and last one that I'm going to present, is essentially a recognition that there are many stakeholders here and they do essentially need to work together. And one journal can take steps XYZ, one researcher can take XYZ. Generally speaking, there's a disincentive to do that, right? Reproducibility is not costless. So a researcher that produces fully reproducible work presumably takes extra time to do that. And so one chain of logic would say they take that time away from other work that could be work that's recognized by the community, like more publications, for example, more discoveries. Similarly, one journal puts more standards on its authors. I mean, some have, but one journal puts more and says, okay, to publish in my journal, you need to do this, that, these extra things. Arguably, researchers would go to another journal. So there are ways in which the community needs to work together. Funding agencies need to think about standards for funding at the same time as journals are thinking about standards for publication. At the same time, scientific societies are thinking about what do I need to communicate to or train my community around reproducibility. At the same time, libraries and information scientists are thinking about how to curate and steward all of this information. So this is really a symbiotic ecosystem. And this is one of the reasons why progress has been relatively slow. This reproducibility discussion has been going on a number of years, although we are making progress. Okay. So I think this discussion points to a couple of interesting directions where we could go in the future. So thinking about a computable scholarly record, I think, is a very natural fallout from our discussion. So we have sort of implicitly been imagining that the scholarly record continues to be PDFs, sort of sitting there, often in siloed and closed areas where you pay $35 to read the paper or whatnot. Now, if we have, let's just imagine we're in a future of radical transparency. We have data available, code, methods, workflow information, computational environment information. We're able to largely regenerate these results, and we have all of those computational steps. You sort of start dreaming about the ability to rerun the code. You never could have done that with the PDF. Well, I don't want to say never. You could have re-implemented it, but it's already implemented in software, right, once. So reusing the code. Applying these implemented methods in new contexts with new data, for example. You could imagine, as we're sharing data, of course, related data set sizes can increase, sample sizes can increase, we can have more powerful experiments, for example. We can improve the validation of the findings. So we have now the ability, if we can run a model, for example, on a data set, say it's an updated data set 1 year later, or a new data set that's been collected, well, there we're starting to do some validation of findings that almost can be done in an automated way, right? Presuming there's conformance in the data and the code can sort of absorb that data as an input the way it did in the past, for example. So validation almost starts to come for free in this world. And it prompts us to think more clearly about our discovery pipeline and how we organize it. So thinking about a sort of entire spaghetti of code that then pops out some results is one thing, right? We would never know, we don't know exactly what the scientists are doing. Most of this is pretty closed, right? That's very different for things like modularizing the steps that might actually be leading to those findings. So for example, in a machine learning context, it may be very useful to separate things like data cleaning, merging, sort of reconciling, normalization, and so on, preparation of the data, with feature selection. That may be a completely different step. And once you have sort of done that, whether it's dimensionality reduction or however you're doing your feature selection, that may be different from the machine learning application and model building that you actually do. So there's 3 separate steps, and I'm just, that's at a very high level. And when I'm comparing pipelines, maybe what I really want to compare is how you dealt with outliers in your data cleaning step. Or maybe the real reason your predictive model is working so well is you're very clever and knowledgeable in your feature selection step. And so being able to sort of parse out what those pieces are in the pipeline, I think can bring greater clarity and understanding to why we're actually seeing the results that we're seeing. So it points to, at least in my mind, a structured dissemination of our reproducible findings in a way that we're not yet seeing. Okay, so here's something that's a little more modest than that lofty goal of the future of radical transparency, which is an idea that I'm calling a knowledge integrator. So I could imagine something like the development of dissemination standards for computationally enabled and data enabled findings that community members agree on. And it wouldn't dictate what tools you actually used to get to those standards, but you would get to the standards, right? So there could be a number of different stacks that are used as long as they're doing things that conform with metadata, conform with transparency, for example. And now, if you imagine a central deposition of these computationally reproducible results generated maybe according to that standard, be open access, open deposit, and then we can grow this computational scholarly record. Now we can think about the integration of new results as actually extending knowledge in a very natural way, because this is all, at least the code aspects are all reproducible and executable. And so now we have this distinction that will emerge with between results, methods, method types, for example, what scientific questions are being asked, experimental types, that allows us to understand and actually analyze this computational scholarly record as a data source in itself. So this step towards reproducibility is actually a step to machine readability in a computational scholarly record. So we can start asking questions like, what is the overall false discovery rate in this particular field, studying this particular question, for example? What is the key question that computational biologists are really interested in right now? For example, we would be able to query the scholarly record, be able to see where this particular data set was used in what studies and what results by some simple queries, for example. Carry out all sorts of meta-science and assessment and benchmarking would be able to be carried out in sort of a less ad hoc way that's presumably more conformant to the actual problems that the benchmark is expected to be testing. So we could do all sorts of much more innovative performance metrics, for example. Okay, so that's the end of my talk. I wanted to sort of present this idea of a knowledge integrator as something that I think in a longer trajectory is part of the vision behind this National Academy's report. And in conclusion, I'll just say that I think it's very clear that scientific projects will become massively more compute intensive. Of course, we don't see the acceleration of Moore's law the way that we have over the last few decades. However, I don't think there's a slowdown in an innovative use of compute technology to accelerate science. At the same time, science is becoming, and research computing is becoming much more transparent. And I think these two forces will be reinforcing. You need the transparency to manage these ambitious computational experiments. Similarly, the computational experiments will become more transparent because of the complexity and the need for reproducibility. These steps admit a computational scholarly record, like, for example, this knowledge integrator that I just outlined at an extremely high level, which is, I think, essential for verifying and comparing findings. So this is the end of my talk, and I think I'm just about right on 30 minutes there. So I'm very happy to take questions.
So Victoria, that was a lovely, thought-provoking talk. There are two questions and a remark in the chat. I don't know if you want to take a look and pick, because I don't know how quickly you have to go, but if you find the chat.
I do have another call to jump on too. So let me just, I brought up the chat.
Yes, have a look.
So is the lens here a bit grandiose? Yeah, but there's a value to being grandiose, right? In the sense that if we can provide a 50,000 foot framing of issues, it doesn't necessarily provide a blueprint, but it opens a door to bringing the community together to start thinking about what that blueprint is. I think you could argue that the report itself with its recommendations is somewhat grandiose. Similarly, those recommendations, what they actually mean in the context of NSF policy, in the context of research, is not yet crafted. And constructing that blueprint is part of what's taking that vision and sort of making it real and actionable. So can the recommendations work when data was collected from sources that are suppressed by a government? There's lots of data that are closed, right? So one of the recommendations says, well, let's start to think innovatively and fund projects that pilot solutions to how to work with data that have less than full transparency, so shall we say, and possibly political associations and so on. So there's certainly challenges around data sharing and also around code sharing for all these artifacts. But this, I think, is an opportunity for research and understanding how do we approach some sense of reproducibility, and even in cases where it's not fully obvious how you can't just simply expose it on the web, right? Okay. Oh, well, thank you. The last one is I think it's a compliment. So this is a pathway for our sort of future. So this is in 30 minutes, it's difficult to not be grandiose, I think, in outlining a vision. This is something I'd be happy to chat with any of you in more detail about. And some of my other talks do go into a little more detail, and we're currently developing ideas and writing papers that are much more in the weeds and provide much more of a blueprint and clarity. But I think this is what I've tried to do is really sort of think about a vision for where we can actually go with some of the opportunities that are arising due to the, you can't underestimate how much the digital transformation has affected different aspects of society, and science is no different, right? It's very much a disruptor and an opportunity for us.
Thank you so much, Victoria. And the audience, please thank Victoria in the chat if you enjoyed the talk. And I'm sure you'll be back to share some more material in the weeds, Victoria, at some other time. Next week, we have kind of a related talk, AI explainability. So that's what we're discussing next week at the same time. So thank you, Victoria, so much again. And thank you.
Thank you, everybody.
Audience.
Thank you, Susan.
And please thank Victoria in the chat if you enjoyed the talk. I'll stop recording now.